this. Yes, I basically yesterday, let me just quickly share. I don't know, but I don't think anybody have problem in opening the SPSS, because when we opened it yesterday, and this is the BMI data. Is it BMI or the skin? This is the skin lesion we did. So, and I said that if you want to open existing file, like now, even if you have opened one, you want to open another one, just go to file. Even if you open SPSS, you click on the SPSS icon. Let me even click on version here, and I will share with you. So the way it will prop up. And you see, when you click on the SPSS icon, see what comes out. So it will give you, by default, you see that it's telling you, look at here, this page, open an existing data source. It's asking you, do you want to open an existing data source? That's by default. If you just say okay, it will just open, as it will open a window for you to now look for the folder where it is located. Therefore, if I say okay now, can you see it will give me something like this? I will now go and be searching. Let's say I cancel, I didn't say okay, I just cancel that thing. I may want to, okay, I want to start new file here. Or if even after I've canceled, if I still want to open existing data, it's for me to go to file and I click on open, no new. Is in open, just new mean you are opening new one, but open, that is existing one. You click, can you see it's the same thing it's giving me? It's for me to now look. So it's you that will now search through your computer. Where did you save that data? That's all. Where did you save the data file? It's you that will know where you save it. You look for it. Like now, I'm trying to search. Okay, I look for the folder where I save it. This icon stuff. Like for me now, it's in D. I'm trying to look for where I save. So everybody, it depends on where you save it. And that's why it's good to save it somewhere. I prefer don't go and be saving in desktop. Though you can say you can look for desktop also, but to me, it's longer journey. People say desktop is easier. You just sit on your desktop. That's if you are not using, but if you are using SPSS, you have to be looking for a desktop. Put it in document where you can easily access it. So data file, can you see now? I will now click on the one I want to open. If it is SPSS, if the existing data source file is not SPSS, if it is Excel or any other one, so you come here, file of type. You see file of type. You see by default it is SPSS. That's why it's only the SPSS file in that folder that is showing you. Others are there, but it should not come up until you now come and click on this arrow and now click the type of data source you are talking of. See Excel. Immediately you click on Excel, all the other form it disappear. You not see them. They are there. They go. You cannot just see them. The Excel one will come up. You now click on it. Like for yesterday, the Excel, when we click on it, let's say the skill list, you just click on it. It will tell you read variable name from the first row of data. Yes, and by default also, it will show you the first sheet. But my own data is only in the first sheet. Some people, the data may be in another sheet, may not be the first sheet. You have to scroll, click on arrow, and look for the sheet that have the data and click on it. But it will tell you read variable name from the first row. So you now click OK. You click OK, it will open. I can share that one. It will open. Can you see? It will open. This is Excel, just open in SPSS. So before we go to that, I think we have demonstrated how we you know, we sorted to change from say format to code it. Does anybody have problem with that? Because what I don't want us to waste time to be repeating myself on what we discuss, everything we discussed yesterday, so that we have time for other things. But another way, I want you to understand if you are having problem with some of the things we did yesterday. So please, maybe I should first of all ask a question. Does anybody have problem? And let me know the areas you are having problem with. Please be sincere, so we can quickly run through that area. So please, I want to give everybody 1 minute to say that. Which area? Please. Which area is not clear on what we did yesterday, so that I want you to repeat, to re-explain, so that specifically I will just go to those areas. So please, let's talk. Or you want me to, or you can shout it to me if you don't want to say it. You can shout it. But I feel maybe the time you are typing, if you just talk. So you can shout it. So Dr. Una, which area specifically?
So I think it's not necessarily, it's mainly the areas of those frequency tables, I think.
Okay, where we run the frequency table, okay.
Where we are running, for me, where we are running the
frequency table, okay. Dr. Judith, any area that is not clear yesterday you want me to quickly touch?
Not really, sir.
Okay.
Just once I need to practice, once I install my SPSS, then I can.
You say your husband is coming today, has not arrived to bring that computer.
Yeah. Sir, the story, let me not even talk about it.
Okay, no problem, because
it's the practice problem. If I can practice, then
have you installed the SPSS?
No.
Please, you know what you tell your husband, let her just buy a new computer now today. It will not cost you more than 150,000 or to 200,000. The one that will do the work. Let you just buy it today and do everything, and just because even you cannot quantify what you are learning, what you are missing in terms of money.
Yes.
Okay. I'm just telling you that. Like me now, if I want to analyze some people, you analyze just smaller them, you just pay 200,000, 150,000. So if I buy a computer for 150,000, I have to do one analysis for 150,000. It has paid for that computer. So Dr. Aman, Dr. Tony, unmute yourself if you want to talk, please. Because if you are talking, you didn't unmute, I won't hear you. Nobody will hear you. Maybe it's not even there because somebody just put the computer and go and be babysitting. Okay.
Good afternoon, sir. Good afternoon, everybody. I'm fine.
Afternoon. Yeah. So any area yesterday you want me to touch specifically so that I quickly revise them before we move to the next work? That's what. Since sometimes you need to call people as if they are in primary school, it's okay. Any area? No area.
For me, no.
Okay.
No, sir.
Dr. Taiwo, any area? Don't say because somebody said no, you say no. Please. Dr. Taiwo.
I'm hearing you, sir.
What is it?
I'm hearing you, sir.
Yesterday, any area?
No, I'm okay. Just I need to practice.
Okay. Prof, sir, Professor Amaitari.
Well, I don't think I have any issues.
Okay,
no,
that's
just like
Dr.
So I think we should move on.
You are welcome. Dr. Nunju. Dr. Nunju. He's there now and he's not. Dr. Nunju.
His network is bad.
He's yet to connect.
Okay, no problem. Yes, it's only Dr. Una. So I will just go straight, so I will not waste time on all those other. Let me just go straight to
add one more thing.
What did you say?
To add one more thing, sir. To add one more thing, sir.
Okay.
Just to the splitting of the data file, is it what we did yesterday where it was
No, we have not
cancelled?
even split it. No, we didn't split. We have not split it.
Okay.
Don't worry. We have not split
All
it.
right.
We do splitting today. We didn't split
Okay.
yesterday. Okay, no problem. Okay, let me just, that's great. Just 1 minute. Yes. I'm just trying to close the one. Okay. Let me share this now. Yes, let me share what I read. You know, I've brought this thing out now. This is the file we were using yesterday, the skin lesion. And no, we were able to do age group. Then we were able to have the cutoff for those CD4 count to say, okay, low CD4 count, CD4 count less than 200. So then we were able to do, how did we do that? We did select. Now, the frequency, maybe I'll just start from the beginning now, just graphical, because Dr. Onashuku talked about the frequency. When you open your data, the first thing you will want to do is to look at the frequency table. So, okay. So the frequency table, you go to analyze. You see descriptive statistics, frequency. So I will advise every one of us, I don't know how many times I will say it. Some of these what we see, this descriptive, all those things, we have covered it in our lectures, and the lecture is on our platform, it's on the YouTube. You can get it through the website. Go and go through all the descriptive statistics, differential statistics, basic concept. You get to know some of those language, because I don't want to be. Sometimes I just feel some people don't even know what does descriptive mean. How does it differ from differential? So descriptive statistics, frequency. Now go to frequency. You now click. So you can. I want to explore every. I will just say Control A to move everything except serial number. I return it. Okay, this one was not part of our this before. Let me return them, because this one was produced yesterday. But the original data are like this. You can just say, okay. When you do it, you go through, you see the frequency table, and you see this age, the sex, marital status, skin lesion. Okay, wait, am I sharing? Sorry, I forgot it. Sorry. Yes, this is it. I share now. And you see age, sex, marital status, skin lesion, CD4 count, viral load. Now, you will notice something, that the quantitative variables, they are listed long. Look at age. You know, all the possible values, only few that are concise. Look at, we have 18, 1, 19. You see, sometimes you may even see some that you only see one that maybe you have a repeated value. All of them, you just list it there, because you know there are unlimited number of possible value in between two given value for quantitative variable. Because of that, for most of the time, continuous variable, it will be a list, so too long. But for categorical, you can see snapshot. Sex is two categories. You can see the frequency. I can easily copy the sex and go and put in the table and say this is the frequency for the sex. The same thing goes for marital status, skin lesion, lesion. All the categorical variables, all the quantitative variable, you get. So you see now, you are with this frequency, you have summarized the categorical variable. The only thing is that in some few occasions, you may have too many categories that, and because the frequency in some of the categories are very strong, you may collapse up. Apart from that, once you just run it, even if you want to collapse, you can do the cleaning and collapse it, or you leave it like that. When you are putting on the table, you collapse it. So whichever way, for categorical variable, it's already summarized by just running frequency. You have already done descriptive statistics for the categorical variable by running the frequency. But it's not true for quantitative variable. The quantitative variable, for you to summarize, you want to know the mean, mode, median. The mean, mode, median, standard deviation. So in order to do that, you can go, there are two approaches to do it. The first approach, it will just show you mean, standard deviation, minimum, maximum. Most of the time, if something is normally distributed, that is all you need for it. Mean, standard deviation, maybe sometimes minimum, maximum. So to do that, you just go to analyze. Under descriptive again, instead of frequency, you just say descriptive again. And you see, under descriptive statistics, you now come to descriptive instead of frequency. You click on it, you can bring out the quantitative variable you want to know this thing for. You click OK. Can you see? Because I'm running it in the result background, so can you see the result for that one? Descriptive. Please, if somebody can see, just talk. Say you signify. Just
yes,
talk.
I can see.
Yes, that's great. So can you see now? It has given us number one. You put n, which is the sample size, the total. If some of them they are missing value, it will not give total for that one. But for all of them are complete because the sample size for this study is 150. So now minimum value for age for each of the three variables I put there give you minimum value, maximum value, mean, standard deviation. That descriptive give you. But you can see for most of the time, when you want to do this, that's all you need. You don't even need more than mean and standard deviation. But you see that it does not give us mode, median. So if you want to get that, you go analyze. Descriptive statistics is that first one, frequency you use. You click on the frequency, you now click on statistics. And click on statistics, you see the options. And you say mean, mode, mean, median, mode. Even the one you don't even need the idea. As many as you can click, minimum, maximum. To me, that range is better. You instead of putting range, put minimum, maximum. Because if they say range is 10, 10 can be between 10 and 20, between 20 and 30, between 30, 35 and 45. So it's good to give a picture of where it is from, where that is still range also. You just give minimum and maximum. And if somebody minus it, you know that the range is 10. So minimum, as if you want to show it, you do that. Then quartile. No, I did that yesterday, quartile. So when you do it, if you, okay, let me do something. I will look at it. Yesterday, I uncheck this display frequency. I will not uncheck it, I will just run it. You see, it will do all these things. I'll click here and also run the frequency again, long list. Now that's why if you don't want it, you say you should remove it. But all the same, let me click. Can you see? It has done it. Can you see that first table frequency? Can you see? It done the statistic for us, mean model. But if you look down, you also run their frequency because I didn't uncheck that box. I talk about display frequency. Because if I don't need, I just uncheck it so that it doesn't display. Now, look at it. You look at age, mean, median, mode. Can you see? We said yesterday is positively skewed. When it is positively skewed, the mean will be the highest value. That is, if you are along the scale, you know the scale go to the right like this. Along the scale, it will be most rightmost. It will be the rightmost value. That is 30. Here now 32, 33.2 is more than 32. median is 30, and mode is 31. So the median is usually between the mode and the mean. The median is usually between the mode and the mean if there's skewness. If it's negative skewness now, the mean will be smaller, the median will follow, and the mode. And I explained the logic behind it yesterday. And we are still going to explore for normality. No worry. So mode, deviation. Now,
Hello.
sorry, the thing just went off. I don't know, you know. I mean, Akwanga, you know, I don't know. And this network was good yesterday. No, day before yesterday, it was making problem when I was in a meeting. Yesterday, it was okay. I don't know. No, just Dr. Nunju, is your network stable now? Unmute yourself and talk. Dr. Nunju. Dr. Nunju. Hello? Dr. Nunju. Okay. You're not talking. Okay, let me go back to what I'm doing. So you will see, if it is, you believe that this thing just want to report the mean and standard deviation, right? If you want to, you feel that it is skewed, you want to report the median, you can report it. Some people also advocate that if you report the median, put interquartile range there. But people, I don't usually do that, but many people, they may ask for, you know, sometimes when you, if you are doing an exam or you are publishing, it's a different examiner or different editor asks for, or reviewer asks for different things. And some of them may make sense, some of them may not even make sense. Short to short. Sorry. Please, I'm in a meeting. You are supposed to be in this meeting. I'm in a meeting later. So you can now show interquartile range. Like you look at the interquartile 25. There are three. I explained yesterday the meaning of quartile. Quartile are, there are 3 points that divide something or a data set into 4 equal parts. If you want to divide something to 4 equal parts, you need 3 points. You need 3 points to divide something to 4 equal parts. Those 3 points are called quartile. No, quartile, there are 3 points. But you know, the word quartile comes from 4. That is, there are 4 equal parts. But that point at the quartile, and there will be 3. The quartiles are 25th percentile, 50th percentile, and 75th percentile. That is 25%. Let's use the word percentile percent. 50%. 50% is the median. Can you see? If you look at it now, the median is the same 32 is the same thing. 50% mean median. So when you report median and they say you give interquartile range, it's actually you are reporting the percentile. That's all. The 3 percentile, 25th percentile, the 3 quartile rather, you are recording the quartile. The 25th, 50, which is the median, and the 75th, which is the 3rd quartile. So that's just it. Now, I think, is there any question? Please, before we proceed, I want to proceed. I want people to be asking questions. Me, I prefer it when you don't just assume. Because that's one of the reasons when you go back to do it, you cannot do it. But you were assuming. But if you try to clarify, you discover that it is very straightforward. Any question, you can let me know. Okay? Now, let's do another thing. We have summarized now. You know, you have summarized for qualitative, quantitative. But even the quantitative, apart from giving out the mean, median, range, whatever, you may want to still put them on a table. You want to group the value so that they will sit like all those categorical variables. So in trying to do that, you need to range them. So I did that yesterday. Oh, okay. Do we repeat it because I did it? Dr. Una, is it part of what you request for? To range again, the way we range the age yesterday to develop age group, was it clear?
It was clear when you are doing it, but to practicalize it was a problem, sir.
You were trying to practicalize it. Okay.
It was a
So if let's say you watch the video, okay, let me just quickly do it again. All we did was to say, okay, you go to transform. Maybe you didn't go to transform. When you go to transform, you know, I told you, if you have group of, if you have quantitative variable, if it is you want to divide it to 3 or more categories, you go to transform. If it is just 2 categories, you don't need to go to transform. You can do it and transform also. They just go to that data and select. That was what I did yesterday for CD4 count. But let's do the transform now, because this age now, we want to group into less than, because the minimum age you can see is 18 and the maximum is 56. You have shown before, minimum 18, maximum 56. Can you see? Now, we want to, you should, I will determine how do you want to range it. Apart from some situations where there are standard range, like BMI now, you know, there's standard range, or maybe there is a standard range for CD4 count you want to use, or viral load or whatever. The age, most of the time, doesn't have one standard. It's you that look at the way the data is and determine the best way to do the ranging. Whichever, whether there's standard range or there is no standard range, it's you that you have to know, okay, what is the meaning, how do you want to do it? You put it in the computer. Go to transform and now choose this option, code into different variables. Code into, there's another option before that, code into the same variable. Don't do that. If you do that, it will form the category for you, age category, and delete the original age you have there. So I don't know why they put the option there, but you get this option, code into different variable. Click on it, it gives you something like this. There's a space here. On this page, you see input. Let me bring the annotation. You see input variable, go into output variable. So your input variable, you click on age, is your input variable, you move it in. Immediately you move it in, can you see now? Say numeric variable, you go into output variable. So that numeric variable now, you say, what is the output? It's asking you the question. You now come here, you want to call it age group. Let me call it age group 2, because I have one age group, the one we have done before, so that I can differentiate. Age group 2. You now want to move it to replace this question mark. In order to do that, you should click change. You may want to label it as you can, you know, this one will not allow you, the age group, the one you put under the name will not allow you for space or something. So if you want to type, label it and put space, you can do that. It's optional. Now, after you have done that, you see age is going to age group. You now come to old. You want to set the new values, old and new values. When you click on that, you now click on range. And click on range. You see, you can start from 0, seeing the lower is 18. That you just make sure you choose a value that capture it. 0 to 19, that is the first group. Sorry, 0 through 19. You now click type 1 here. Look at this space down. When you type 1 immediately, the hard, you just highlight, you add it to that place. Is it clear? Then come back here, 20, the next one will be 20. If it's something that has decimal, you have to account for, like if it's BMI now, we will say so to 24.99. Then from 5 to 39, 29.99. You have to account for that decimal. Otherwise, if you don't do that, you just use whole number. Any number in between that have decimal, you miss out. But this one, the age is whole number. So you can just say 20, 29. You had 2. Is anybody talking? 30 to 39. So, did you reach this place stage, Dr. Una? Did you reach
No,
this?
sir. But I'm clear here now. At least I
So,
understand.
let me just listen and just leave it. 30 to 39, 40 to 49. So, where was the problem? Oh, where was the
I didn't
problem?
enter the transform. The transform. I
So, you
follow
didn't go to transform. If you have checked your module self, you will have seen it there, because in the module also everything is well spread out. So I now talk about how you go to when you do it. The thing is there. If you go to data editor window, you go to data editor window. Sorry, you will see there. Can you see? Though it's the same thing with, we have done the age. That's why I call it age group too. So if you want to remove this dirty decimal, you go to variable view and reduce the decimal to 0. You see that decimal is no more there. And if you run it now, it will give you, okay, let me see. Come look at something. If you go to view, this at the left upper corner, after edit, you see view, you click on it, click on variable value. Can you see? Can you see? All these CDV kind, you see 1 and 2, in 1 and 0. The value are yes and no. It comes out. The age, we label it. But if you look at this age, we didn't label it. You have to go on, because after you have done, if care is not taken, by the time, if you don't go and label, you even forget what's 1. What did you code as 1? What did you code as 2? You forget. So it's good to go back and go to in variable view, to click on the values and now see, say 1. What I mean by 1 was these people that were less than 20. What I mean by 2 are these people that were 20 to 29. What I mean by 3 were 30 to 39. What I mean by 4, 40 to 49. What I mean by 5 are greater than or equal to 50. Anything greater than or equal to 50. I told you yesterday, I don't use it like that. I go and go to the Word document and copy the sign and come and paste it and work. So if I want the way that I put it here now, I can just copy this one and copy it and go and paste here, because it's the same thing. Look at it. So when you come back here now, can you see? It has labeled it. But if you don't want to be seeing the label, you look at all this skin lesion, yes to no. The labeling is for anything categorical. When you group age, you group something quantitative, it has become categorical. The age is different from the age group. The age is quantitative, continuous variable. Age group is categorical variable, and it's an ordinal variable, in the sense that when you group something that is quantitative before, now group it into more than 2 groups, 3 group or more, is ordinal. If it is 2 group, is nominal, is dichotomous. Dichotomous or binary. Anything nominal that is 2 group is dichotomous. But if it is, look at those CD4 count. It's a variable, is yes or no, it's dichotomous, nominal. But if it is, let's say we put into 3 now, CD4 count above 500, 200 to 500, less than 200, if we are having 3 group, once you have 3 or more category, it will be ordinal. And you can only do that one through what I just did for 80 now, through going to transform and do that. But if it's just to divide it into 2 like that, you can do it in that place, but it's not necessary to go. Just go to what we did yesterday for the CD4 count. Let's say we want to do for viral load. We want to talk about high viral load. What is high viral load? Viral load clinician. Viral load greater than what is considered high? Please. What viral load is considered high? Because me, I have forgotten that. Clinicians, what viral load is considered high? Greater than what? Oh, Dr. Laggo is on here. Okay, I'm just
greater than 1,000.
1,000, right? Greater than or equal to 1,000.
Yes, sir.
So imagine
Yes,
now.
sir. High is greater than 1,000.
Oh, greater than 1,000. Okay, now I may want to know high viral load. People that I want to just separate them to two. The high will be on one side, the other people will be on that side. You don't need, if you go to transform, you can do the same thing, but that one self is waste your time because you have to know so that you can capture maybe what I say from 0 to this, and but it's wasting your time. The best way to do is just say data. Go to data. Split nodes. The second to last option, select cases. You click on it. By default, what you have there, all cases. That is why all cases are being analyzed, because by default, all cases are selected. So you now say if condition is satisfied, click on it. Immediately you do that, the if under it will get highlighted. You click on it. It give you this calculator, is it keyboard now? We can call it. Now you now move that variable viral load inside. Just say greater than, this is the sign, greater than 1,000. Tap it there. Click OK. You see, if I share the data editor window with us now, you see, if you look at the data view, all this line they cross here, he has selected the one not cross, they are the one that the viral load is greater than 1,000. The one that are 1,000 and less, he has crossed them out. If you run any analysis now, it's only going to be for only those who viral load is greater than 1,000. Okay, let's say we want to do what we want to do now. Let's just run the skin lesion. Let's say we want to run the analysis frequency of skin lesion. No, I want to move this thing back and put skin lesion alone. So let me share the results. Can you see? It's only 22. Yes. It's not like, you know, the people that have high viral load, they are the one that will have low CD4 and they are the one that will likely have skin lesion, because this study is about skin lesion in HIV. So people that will have skin lesion as a complication would be those who that have high viral load or low CD4 count. And he's telling us here that all of them, there are 20 people. What we are seeing here, 20 people have viral load greater than 1,000, and all of them happen to have skin lesion. So it's only 20. So I told you this method of just having the cutoff is for two things. It's for you to just, okay, you want to select some people for analysis, for the analysis. That is what you have just seen now. Even the purpose for it is what is to use it to create a variable which is high viral load. That's the variable. If you can come in now, I go to, you see here also, at the last column, you see filter. Those ones that is selected, that have high viral load, greater than 1,000, they put selected here. The value is selected. So that selected mean one. The one cross out are the one that don't have viral load. Those ones that have viral load 1,000 or less. They are the ones that are cross out. You see, non-selected. So this not just a matter of computer that liberate. Look at it. If you go to that view and click on value, can you see? That's one selected is 1, and one not selected put is 0. So it's actually has created a variable for you. That is this variable CD4 can greater viral load greater than 1,000. Yes, mean 1. That is selected 1. 0 not selected. So you work on that logic. If you work, you just go to variable view, go on that filter, the same thing you are showing here. Look at it, the last column. This is the variable view here, filter. You now change the name of the filter to high viral load. Okay, yes. High viral load. So when you create this one, this is the what is written in label here. Is that command I gave? High viral load greater than 1,000. You can delete it out. If you don't delete it out, inside the component it will be showing the name. You remember this place for labeling. This label will be shown as the name, but you don't want it. You want this, what I wrote here, high viral load. You can as well write it here also. Come and write it here and say high viral load, but you don't need, you can remove it. Or you can repeat this thing, but that one is showing it. So look at it. The value is 0, you remember is not selected, 1 selected. That is high viral load selected. The one that selected, you give them 1. So that will be the yes. That is high viral load greater than 1,000. So that's a yes. Now change this and change the other one. The not selected, set it to no. So you have created a variable, high viral load. Just like the way we have created low CD for can. That is the way they create diabetic. The blood sugar, let's say this data has blood sugar now. Because the blood sugar, just click on blood sugar, say greater than or equal to type 120. You get the same. You now come back and change that filter to diabetic. And I change that selected, not selected to yes or no. You have created it. So if you want to go further now, you have to come by that thing he did. It has not removed the crossing. So you have to go back to data view, to data, not data view, to data, and click and I'll say all cases, back to all cases. Immediately you do that. Can you see? You will see. You will see that that thing is no more. That thing that so that deselected anything, it just created a new variable for you. If you want to analyze that new variable, now analyze frequency. Now, frequency, you have to remember something. Remember, you want to run this frequency, but you may have to go and cancel all this because if you don't cancel it, apart from running your frequency, you go and do mean mode and median for it, which you don't need because it's not me. You cannot do mean mode or median of coding because that is coding. It's category. It's a categorical. You want mean mode and median for this viral load now. You will then just do mean for 0 and 1. They will give you maybe 0.1 or 0. something. So you don't need that one. That one is not applicable here. So you have to go and check it. Whatever procedure you did last in the SPSS, when you go back to that function, it will still retain it unless you remove it. When you say continue, that's it. Okay. So can you see? Okay, let me share the output. You see, high viral load. Yes, 22, that's 40.7%. 128, 85.3%. That's how to do it. I think this is virtually all we did yesterday. This is where we stop. So let's move. Any question? So that we now go to splitting now. We want to split. Any question on this one we have done?
Sorry, sir. A quick question on the interpretation of that table. The previous table where you showed the selected cases and how it impacted on skin lesions. The frequency was 22. This one. So the interpretation would then be that.
The interpretation
22.
22 of those. How many people have skin lesion among the people that have
high viral load?
Yeah. But it's not happened that all of them 100% have skin lesion. If it's not 100%, what will happen? Because there are 22 people that have high viral load. If it's not all of them that have this thing, maybe it's only 8 of them. Yes will be 8. The remaining one will be no. See, so far it's only yes that is showing. It shows that all the 22 have skin lesion. Does it make sense?
Yeah, so all those with high viral load also have
Yeah, that is it means that they have skin lesion.
Okay, thank you.
If were to be maybe okay, let me go back to that this thing. Let me go back. I want to select those one also that will have viral load and now run their sex to really know the sex distribution. Let's do that. Let me go back to data. I will just say if condition is satisfied because is that thing, the condition is already there. That's the last thing I did. I just say okay. So if I run the analysis now, analyze, I want to run analysis for this one now is for sex. I want to know the sex distribution of people that have viral load. I don't know. Can you see the result there? Can you see the results? If somebody can see, just talk.
Yes, I can
Yes,
see.
you see.
Yes.
Can you see now? Because there are 22.
Yes.
The denominator, you only selected people that have high viral load, and there are 22. Their sex distribution: female 16, 72.7%, and male 6, 27.3%. Does it make sense?
Yes. Thank you.
I want to
But this one has no
question,
meaning. This type of analysis I just used to demonstrate to because people go and oh, can you see women have more this thing, high viral load than men. It's possible women have more viral, but you cannot put it on this thing unless you run for the whole something. Now go on. Somebody wanted to ask a question. Dr. Yuna wanted to ask a question.
From the output table, sir.
Yes.
One cannot really see that it is it's saying that it's trying to do the sex distribution for those that have high viral load. It's just how do you show that it's actually those that just had high viral load that just this frequency table is
it's you now. It's not that you don't need, it's not show anyway. If you look at the page above this frequency, you see some computer filter, high viral load greater than 1,000. All those things is there.
Okay.
Save the output.
Okay.
But it's you that is not the computer that is you that is it's you that put it. It's you that select. It's just like okay. Let me do another thing. I want to select. Let's select only female. No, we have just used example of quantitative variable how you can select, but you can do the same thing for categorical. I may say that I want to run this analysis for only male or only people that are single, only that are married. Do you get the picture? So I will just select for further analysis. It's just like you may see, you may ask a question and say that how many, what is the, I see rich menopause if it's a female. You know, you are doing your survey among male and female. They now ask a question that is only female that can answer that question. Or what is when is the menarche? When it was the menarche, at what age was the menarche? You know that's type of question only is applicable only to female. In that situation, you select only female and run it. You get it now. So let's see. I want to select only female here now. Just to the same place. If condition is met, instead of this one, I'll just move sex. You know the way you code sex here. I think we code female as 2. That's it. Sex equal to, this one is not less than, equal to 2. You have to know how you code sex. In some situation, if your sex was entered as string, you know what I mean by string? If it is male, female, or else, and this thing, what you're going to put here, you have to put this thing. There is that thing is not, it doesn't, the computer doesn't, the keyboard you are seeing, it doesn't have better. You use your own keyboard. That double this, the quotation, is it double one? Yeah, this is single, the quotation, I think it's single one. Yes. No, I think double one. You quote, I say F. You answer me now. If you don't code, if it's enter as a string, if you don't, if the computer will not accept to say error. But if you do it, if it's enter as a string, you now type, you put like a quotation, put inside quotation, and now type the string inside. The way you write it, So that is why you usually make it easier when all your categorical variable you are able to code them. If you just know the figure that you are looking for, the value of that something, you just put the figure there. That one, if it is figure, it doesn't not require that thing. But of course, there are some few occasions where some this thing may come, like when they has other ethnicity or the ethnicity, they just give you a long list of something, and you don't even want to code good code because they just type it as additional thing, and you now see one that is major, then you want to single it out. All you need to do is to look at the way they type it. If it's in lower case or the way they type it, if it's case sensitive, if you type it differently from what it is not like a picture, the way they put it there, if you don't put it like that, the computer will not, you not get it. And that is why it's better you code your categorical variable 1, 2, 3. You make it easier. So I've selected female now. So if you look at it now, if you go to your data editor window to look at it, what we're running, you see, can you see? It's only the female. Look at it says the female are coded. I think the female, we coded the female 2, yes. No, is it 2? It's 1, no, sorry. It's 1. It's 1. We coded the female 1. Yesterday went up, I was yeah, it's network, yeah. Okay. Sorry, my network. Very chatted, it must be network. Yes, sorry. So I have coded it. Can you see? Can you see the female, the 2?
Yes, sir.
So the female are 1. So the male are cancel out. So if you look at the filter here, examiner, but we are not interested in that because it doesn't show anything. We are not creating. You cannot say you are going to make male and female. Male and female is already there. You can only use that type of thing to create new variable from quantitative variable. It's for selection. So what it just means that we have selected female out. So if you want to say, let's look at skin lesion, maybe a particular, let's do skin lesion, prevalence of skin lesion among female now, and run it. This skin lesion or anything you want, any analysis you want to do, even viral load or whatever, you may want to look at among female. So let me share the output. So you can see, you see. So it's telling you because there are 95 female. So 45 have skin lesion, which is 47.4. 50 do not have skin lesion. That's 52.6 of them. So any question about this selection or whatever, if you, let's say you want to select his marital status now, you want to select marry, the one you want to marry, how do you call it? That's the value you're going to put there. You select that. And you can select 2 things also. Yes. Can you see we can select female that have skin lesion? How do you do that? Can you see when you go to data, you want to select female that have skin lesion. So sex, female, yes. We now put, and we know it's female. There are 2 ways. I discussed this thing when we were giving lecture. Please go and watch the lecture, probability and normal distribution. I talk about the Boolean logic, and you use it during analysis. Or if I want to know, okay, I want to know only the female that has skin lesion. Only the female that have skin lesion. I will now select sex is equal to female. I will now put and this, and skin lesion is equal to 1 because skin lesion, yes, is 1. Skin lesion, we now move it, is equal to 1. I've selected those 1 now. If you run any, if you want to know how many of them, so we can go on. In this case now, you may create another variable from it. That is female that has skin lesion. You'll be able to know. So it has selected it for us. If let's say it's either the person is a female or the person has skin lesion. So that is all. Okay, for example, we want to say, okay, let's talk about, we want to know those who have skin lesion, high viral load, and low CD4 count. Can you imagine? The people that have any of them, any of these conditions, if we want to use them as proxy for people that require treatment advanced stage of the HIV. Imagine, we can say, okay, data, select, now go there, now say, okay, look at 3 criteria. Skin lesion is equal to 1, that is the person has skin lesion. You now put score, you now put all, because the keyboard does not have it, but if you put it there, it recognizes it. Or CD4 count, remove it. CD4 count less than 200. Or put it viral load, remove it, greater than 1000. So if I want to now know, I can go back. Let me go to data editor window. What is this thing? Data editor window. So if you look at it, can you see it has marked those ones you see, that's the mark, those are the ones selected, but that's not the issue. Look at the filter. So I can now go to variable, something, and I say I can call it what do advanced disease, HIV, advanced HIV, or you call it AIDS. Maybe that's how you want to define. I'm just giving an example, AIDS, or advanced. Let me call it advanced. So, that's the way. Oh, that's it. Somebody define it by saying this, advanced disease. I remove this. So if you look at, if you leave this one, it will still give you, they don't like this. You just want to change to yes. The selector is yes. Change. The not selector is no. Change. So now, if you want to run it now, make sure you go back and remove that. You say all cases, because in this case, if you don't do that, it's only the yes it will show you, because it's the yes, that's the one you selected. But you have used it to develop, just create a variable. So when you want to run both yes and no out, so you want to run all the cases, now go back to select all cases. When you have done that now, you run it, analyze. Let's do the frequency of advanced disease. Can you see? Okay, let me share. Can you see it on the screen? So the people that have all those conditions, 3 conditions, at least one of them is 70. But if you want to say and, if it is and, it will take person that has all the 3 conditions. That one will be smaller. That is the person that has skin lesion, then high viral load, low CD4 count. That is high viral load above 1,000, CD4 count below 200. So the person that will have all the 3, it will be small. But this one is person that has at least one of the 3. So some of them have the 3, some of them have the 3 of them, some of them have 2, some of them have 1 of them, but at least 1. That is all. But if it is all the conditions must be met, that is and. Is there any question concerning that? This is the logic we use if you want to know the prevalence of hypertension. You know, hypertension is defined by 3 in your study, by 3 variables: history of hypertension, systolic hypertension and diastolic hypertension. In fact, when you are doing your study, somebody may be hypertensive, but you measure the blood pressure is okay because it's on treatment. It doesn't make the person mean the person is not hypertensive. So in that case now, when you want to now define what is the prevalence of hypertension, you now say, is it hypertension? Yes, you select. Or systolic hypertension greater than 140, or diastolic hypertension greater than 90. When you do that, you now well, hypertensive, now yes or no. So you now label that select, not select, yes or no. You have already sorted out people that are hypertensive and people that are not hypertensive. Any question concerning that? We'll proceed. Any question?
Thank you very much, sir.
Welcome. Yes, Shido, are you have question?
No, I'm okay, sir.
Okay, that's it. Okay.
Thank you very much, sir.
Okay, well, welcome.
Thank you, sir. Yes, sir. I was trying to get that. So the one you're explaining now about, deciding on, okay, the people that are hypertensive, are you talking about under transforming variables into, or which topic is this?
Well, is it transforming per se? It's not under transforming. It's under select. It's under, you go to data, select cases, if condition is met, and now define your condition. It is used to define your condition. Under data, select cases, if condition is met, define your condition. So I mean, yes, what do you say?
No, I was saying that's the condition you were trying to explain. Is that how you write it? That's how you type it.
You do it. That's the way you do it. If you remember, if you were in the lecture when we were talking about probability and normal distribution, when we talk about probability, when I talk about application of hand or the rules of probability, and multiplication rule is hand, addition rule is how. So and I say is used in Boolean logic. Boolean logic is used to search. If you want to search in search engine, if you are looking for, like now, you want to study obesity and hypertension. So if you want them, in obesity, anything obesity, they will make mention of hypertension. In anything hypertension, they will make mention of obesity. If you want to get any journal that have made mention of any of them, it is all you use for either obesity or hypertension. So some of them will be only obesity, the main mention of. Some of them is only hypertension. Some of them, both of them. Whichever way, all we capture for you. It gives you more. If it is only you want people that make mention of both obesity and hypertension, you now say, and in that case, it narrows down. It's only a few.
Yes, only the ones that have
obesity. Do not pick it. You don't mention only hypertension. It has to be that the main mention of both obesity and hypertension.
Both of them has to be there.
That is hand. That is because they are, thank you, both of them. That particular person in that journal made mention of obesity and hypertension. That is hand. So in that case, it's few journal that will come to you because it has filtered. Yes, but if you say all, it will give you more. So it's the same thing when you are doing analysis. If I want to know only those people that, if I want to know only people that have both systolic, diastolic, and history together, I'll use and. That is and it will narrow down. There will be few. But if I just want to need any of them, at least any of them, I'll use or. In that or, that is the addition rule. You gather many of them. So if you go back to even the slide is on the something else. No, I keep on mentioning. Somebody called me today. What will I do? Because some of these things, when we are doing this practical, there are some of those lectures we have given before that give you understanding. Those are the theoretical background that give understanding. We have talked extensively about them and demonstrated them. So if you go and watch the video, and the slide also out there, you get the slide and go through. When you go to you'll be able to understand, because when we are trying to achieve something here now, you cannot begin to give extensive lecture for everything. Yes, any other question?
Thank you, sir.
Any other question? Okay, we proceed. Now, so nobody want to share today. Does anybody want to share so that we proceed? Does anybody want to share so that the person will I will be telling the person what to do. Who is ready? Who is ready to share?
I am, sir.
Okay, Sido. Okay, at least your network is stable today. Oh yeah, share the same file. The same file. We have already even saved it yesterday as disk lesion as SPSS. So just go there and pick it. Even if you just go to that file, you don't even need to open SPSS. Go to that file, double click on it. It will open the version 25 for you and open it and now share for us. Yes, I mean now. Just first of all go to that folder where you save it. Double click on that skin lesion SPSS file. It will automatically
open on my desktop, sir. Yeah. It's already open on my desktop, sir.
Okay,
so
no problem. Double click on it and share with us. Okay, let me allow you to share. So you can share now. Because the next one, we want to split file now. So that we do splitting file. Then we now go to explore. After splitting file, we go to explore. That's where we want to explore for normality and all those. Yes, that's great. Okay, you can click on anywhere, whichever way. You are in variable view, you can go to data view, it doesn't really matter.
Okay, I'm in variable view now.
And you click on data view, just click on data view.
Okay, it's on data view now.
Yes, that's great. Now, imagine we want to do this analysis. Let's say just take our sex and skin lesion, we want to run it. I just choose the categorical variable. Sex, marital skin lesion, want to run it for, okay, let's say we want to run with marital status and skin lesion for male and female. So we want to run it separately for male and female. Marital status and skin lesion.
So what am I supposed to do?
Yes, I'm just explaining, I'm coming.
Okay.
So go to data now, data.
Okay.
You go to split file. It's above that select cases. Just down, third to the last. Split file.
Yeah, split file.
Yes.
So
now, if you look at it, by default, analyze all cases, do not create group. I want you to do something. Click on the third option, organize output by group. Now move the sex. Sex is your group variable here. It's sex you want to use to separate them. So move sex to that box. It was when you click on that thing that the box opened. Now,
yes,
click OK. Click OK. You are splitted by sex by doing that. Click OK. So when you click OK now, you can, if you want to do, the same thing. But if you can achieve the same thing by come to variable view. Come to variable view. Go to the last row, the last, under sex, click, under sex, the last row, the last column rather, the last column, the row, the put row, under sex, click on it. You see split as an option. Can you see? The last one. Yeah, don't do that again, because if you do, see, it's like double split. It's okay. Leave it. I'm just telling you that's an option also. Okay. Come and do it. This is split here. But I think it's more better you do it the other way. The one we just okay. Now go and run analysis now. Go to let's analyze marital status and skin lesion. Analyze frequency. No frequency. Marital status, skin lesion. Click OK.
Okay.
Yes, sir. So go and share with us. You can stop sharing and share the output. Stop sharing this one and share the output. Sometimes you can share again, but sometimes with SPSS, you'll be looking, we won't see this, or if you want to share again. But it's better you stop sharing this and now share again and now go to the output.
Can we see it now?
Yes, you can see it. Yes, that's great. You will see something first. Can you see sex female? You will do the marital status. Scroll down. He did the mythical status and did the skin lesion for sex. Can you see? Sex female. Then scroll down. Sex male. He did the frequency separately.
Okay.
Can you see? Hmm?
Yeah.
So you run the
Yes.
frequency, give you the output, male and female. So this is what you do if you are, especially if you're, this is comparative study. There are two groups. You want to analyze separately for the two. That's how you split and now run the analysis separately. But this one is not as neat as the option you want to. Go back to that data. Go to the, click on data here now. Click on that data here. You want to, then go back to that split file. No, not that one. The one up.
Okay.
Yes.
That's this one.
Yes, yeah. You know, if it is data view now, you will not see split into five.
Okay.
Click on compare group. This the option in the middle. Compare groups. Yes.
Okay.
Instead of organize output by group, click OK now. Click OK. Click OK. Yes. Now go and run the analysis again. Go back to analyze. Let's run the analysis again. The one you run, you're going to see what will happen. Frequency. Just click OK. Because the, so can you see what he did?
Yeah.
You see
Brought
for
them
item
together.
status, he put them on the same table. Male, female on the same table. Scroll down. Skin lesion. Put them on the same table. Can you see? Can you
Yes,
see
sir.
this option is neater. Instead of
Yes.
scattering, it's neater. So this is the option you should be using. I just demonstrated so that you see the difference between the two. So,
Yeah.
so if let's say it's a comparative study now, you see group where rural, urban, you see them side by side there. You'll be able to, that is how to split file. Simple. If there are three groups, it doesn't matter. Once the variable has defined the three groups, you just put use to split, it will arrange it for you. If it is urban, rural, suburban, semi-urban, all of them will be there and separated like that. That is splitting file. Now let's explore. Want to explore. Now go to any question on this splitting file on any angle. Okay, we want to explore. Go to, when we say explore, in your descriptive status, you want to explore your data, as a quantitative variable for normality. No, though we have already done some better, there are much to do with the quantitative variable to really know where it is. Go to analyze. Descriptive statistics. Then you see under explore, after descriptive, you see explore. Yes. Move age inside that dependent list. Click on plot. Plot. Click, you will see by default, stem and leaf is check. Leave it. Check, also check histogram. Histogram. Then you see normal T plot with text. Click on it. Click continue. Click OK. Scroll down, you will see the result down. It's still coming. I mean, your RAM is not much. The RAM for your this is not much. Okay, sorry. You won't split. It's going to, you know what? That's one of the things even slow also. Go back to that data and don't split again. Go back to that. You know, what we have just done is going to do it separately now for this thing. And that's why it's taking time. Data, I want to explore it together. Go to the split file.
No, I didn't get you. I should go to
Go to data and go to split file. Where you split file? Yes, that one.
file.
Yes. Now, all analyze all case. Click the first option. Analyze all case. Do not split.
I've done that.
Yes.
Okay.
Okay. Click OK.
I've done that.
Yes. Now, that thing is not coming up again. Is let's see your output. Is it your computer that is slow like that? It's still running.
The same
Your computer,
running.
your computer is the RAM is small. Yeah. Stop sharing. Stop sharing.
Okay.
Stop sharing. Let me use my own now. Now that your computer is just coming up, let me use my own. So what we're doing is to analyze, descriptive, explore, age into dependent list, plot. You by default stem and leaf is checked. You check histogram also. You check normality plot with test. You continue.
Sorry, sir, what's that factor levels together about?
What do you say, ma?
On the box plot, the factor levels together.
On the box plot, okay, box plot. Yes, factor level together. Where they say levels together, where there's a place actually want to spread by factor, but there's no factor splitting them. That was just what this one just okay, dependent together, dependent together. Well, okay, maybe we should take it. I don't actually know what that one means. Then let's first run it. We can come back to see that dependent together. Then you click on this and click OK. So look at it. Can you see? Let me even first of all clear this. No. Let me rerun the something.
So it's showing on my own now.
It's showing on your own.
That's finished.
So, okay, you want to show us and you stop sharing, right? But you have to repeat, okay. Share, you have to repeat it. Cancel it. Cancel, just don't save it. Cancel it and let's repeat it with your own because that one we split it. So, go to give you too many things. No, we've split data. We didn't.
So I should
Okay,
share screen.
it. Share it now. Share it. I'll stop sharing. Share it because I wanted to start explaining the output.
Can you see my screen now?
We can see. And let's see what is showing now. You know, it do it 2 by 2. So I don't want that one. Clear what I'm saying now. Clear this output. Cancel it out. Cancel from output. And if you want to save, say no. So that it will
close the output.
Cancel yes. So that I can say no, 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 no. Now go back now. Share again and now run it. Share again. Quickly share.
I should share screen.
Share the screen and share your SPSS. Just share that your this thing. Yes. Any of the windows. Either so go to analyze. Go to analyze. It will not take time.
I don't know why it's
freezing.
Okay. It's freezing a bit. Okay, it's showing now.
Go to descriptive statistics and explore.
I'm there.
Just okay. Just say okay because that's what you have done before. Just say okay. So unshare and share the screen for us. The output.
Okay, you cannot see it. It's true.
No, we will not see unless you unshare again and share again.
Okay.
I just want because I like it when one of you is doing it. It makes you to know it better.
Can you see it now?
Yes, you can see it. Yes, you can see. Yes. Let's start from the beginning. Yes. Scroll up small.
At the end, sir.
No, it cannot be at the end. That your this is slow. It's slow. It has not come up. You
okay,
know
me,
what?
I should scroll down. I should scroll down.
Yeah, that's it's okay. So no, okay. No, let's see the first table. Is the first table want to see? Want to see the first table very well. Just scroll, move up so that you can see the table very well. It's okay. It's okay. You see the descriptive table. Can you see the table? Descriptive. The mean. If you remember the mean, 33.2 for the 8. It give you 95% confidence interval of the mean. Then it give you trim mean. Give you median. We'll remember median the right time. Yes. Give you many things. Minimum, maximum, range, interquartile range. You remember. So all this were given. Now you see the mean and median. They are different. But you will see that there's 5% trim mean. The trim mean just means that 5% trim means that they take the middle 95% of the data and use to calculate the mean, neglecting the outlier on the 2.5 on this side, 2.5 the upper side, taking outside 5% outliers. They exclude them and now use the middle 95% of the data to calculate the mean. In that case, the mean is now closer to the median. Can you see the mean? The original mean is 33.2. This one is 32.789. It's closer to the median, the trim mean. Okay, now let's scroll down. Let's scroll down. Let's go to the next. Wait here. Look at test of normality. The test of normality, there are two types that you use here. Kolmogorov's phenol or Shapiro-Wilk. Both of them, this test for whether your data set is normal or not. You know, the computer, the software has a normally distributed data inside the software. So what it does is to compare that normally distributed data with your own. That one is perfectly normally distributed. When you compare with your own, if your own significantly differ, it will be, the p-value will be low. Look at the p-value now. This sig is the p-value. When you see sig in SPSS, means the p-value. So the p-value is 0.0, that is less than 0.001. So even for both tests, it shows that this data set is skewed. It's not normally distributed because it's significantly different from the normally distributed data. Let's move on. Any question concerning that? If you want to test, you know, every other thing, you're going to look at the picture, and those ones, they just looking at it does not quantify it. The skew mean is greater than the median. We know that it's positively skewed, but it does not quantify it. It is tell that quantify it. Okay, let's move. Let's see the histogram very well. Can you see the histogram? Where is this skew to now? From the where does this is this skew to? I want you to talk. Where
right.
is this? It's skewed to the right.
The right, sir.
Yeah, it's skewed to the right. So scroll down. Let's see stem and leaf. The next one, stem and leaf plot. And see stem and leaf. Wait, you will see stem and leaf and the histogram is the same. So look at, it's only the stem and leaf is tilted to the side. If you look at the shape also, like this, it's tilted to the right. But it's just tilted to the, you know, it's tilted on the, standing on the, not on the base. It's standing on the side. So it's the same shape. The histogram and stem and leaf, and it's the same thing. You look at it, it's the same thing. But the only thing is that the stem and leaf give more information than histogram. How does it give more information? The stem and leaf also give you the data. You have access to the data. If somebody publish histogram now, you just see the shape. But if it's published stem and leaf, it will give you the shape also, just like this. Then you can get the data from the publication and go and run the analysis. The data for that variable is there for you to write it out. Now, what stem and leaf does is that it will take the last digit as the leaf, the initial digit as the stem. The initial digits may be 1, maybe 2, maybe 3. Like for this case now, this one is age, and there are 2 digits because nobody has age up to 100 among them. There are 2 digits. So the first digit is the stem, while the last digit second digit, which is last, is the leaf. If let's say we are measuring height now, that we usually have 3 figures, height. The stem will be the first 2 digits, and the leaf will be the last digit. Now, in this case now, what you are seeing here is, say, look at this frequency, you see stem and leaf. The frequency, this number 1 means only one in that category, and that one is less than, actually less than or equal to 18. That is the one that has 18. Now, this one in this category, and that one is 19. Can you see? 1 is the stem, the 9 is the leaf, 19. This one here, the 2 is the stem here, 1 is the leaf, that's 21. Here, there are 8 of them here. 2 is the stem, we have these 3 that are the leaf. So this is 23, 23, 23, 23, 23, 23, 23, 23. This one that I hate here, this is 24, 24, 24, 24, 25, 25, 25, 25. Here there are 11 here, this is 26, 26, 26, 26, 26, 26, 27, 27, 27, and so on like that. That is the way stem and leaf is. Any question concerning this stem and leaf? Are we together?
Yes.
Yes.
Yes, sir.
Yes. You have question, right? Any question? No question from any quarter? Sometimes, I don't know.
My question, sir, is on the test of normality.
Okay. Okay, throw up Hugo. Throw up that test, that table that shows test of normality. Okay, it's okay.
I didn't quite follow, but this stem and leaf part is very clear.
Okay. The table, what is the problem with the normality table?
You said there are 2 ways to assess it.
But you're not clear. The thing is breaking up.
Test for normality. You mentioned the
Homogeneous phenomenon and Shapiro weeks.
Hello, sir. Can you hear me now?
Yes, I can hear now. What was happening?
Hello.
We can hear now. We can hear you.
So yes, sir. After you mentioned the 2 tests, how do they apply? Because you now said if it is showing a p-value of 0.6, it means it is
you open
huge.
radio, television there. What is happening? Your voice is breaking again. We can't hear you very well. What's the problem?
Okay. I don't know. Maybe because my battery is low, I'm trying to.
No light in your place.
I'm connected to a charger. I don't know whether it's a charging point. So let me send SMS. Let me send it as a message to the group.
I think I got what you are asking. Yeah, what I just say, interpretation of the result. These 2 tests, just like I can go, they are testing the same thing. But they said that maybe one is more sensitive than the other. Let me send it, okay? Are you listening now? I hear you. So, what I just said, was that the computer, the software, has a normally distributed data. Yes, that interpretation I'm telling you now has a normally distributed data there. So what the test done, the computer does, is to compare the normally distributed data inside the software with your own. If your own is normally distributed, there won't be difference between them. But if your own is not normally distributed, it's skewed, that will be different. And you know that whenever there is a statistically significant difference, the p-value will be less than or or equal to 0.05. You can see the p-value here now. That's significant. This sig is the p-value. That's how they write this p-value in SPSS. This SIG is the p-value. So it's 0.000 here also. 0.00 means that that shows that it's far less than 0.0001. The significant, that shows that your own is significantly skewed. That is significantly different from a normal distribution. So the skewness we are seeing that we skew to the right is significant. Now this interpretation, that's all. We already seen it even from the table that the mean is greater than the median, and we have seen it also from the stem and leaf and histogram that is skewed to the right. That is, the mean is greater than the median. But we just want to see, is it significantly skewed? And this test has just done that is significantly skewed. Once the p-value is greater than or is less than or equal to 0.05, is significantly skewed. And that's what the interpretation is. Is it clear now? Okay. 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 Go scroll down, Dr. Dr. Shido. Okay. Yeah, good. We have. I think we have explained. People do have brain. Let's look at QQ plot. This is what they call quarter plot. No, we talk about quarter the other time. Those values that divide the data set into 4 equal parts. The quarter, there are 3 of them. So what the computer does is that they have quarter of normally distributed data inside. It's the same normally distributed data they have. They compare the quarter, they plot the quarter against your own. You know, and this diagonal, there's a line in the diagonal. Your own, the expected normal is their own. Observed value is your own. Our own, this data set now is the observed value. The expected normal is the one for the normally distributed data software. Now, you remember in a tug of war, if the two sides have equal strength, the thing will not move from the middle. So we expect if your own is equally normally distributed, all this point, because this dot you are seeing is where the value for their own meet your own value. So if they are normally, all of them should be along perfectly on the line. Some on the line, close to the line, where some are off the line. And we have more. We have some that are off the line below. Those are the ones that are negatively skewed. You have the ones that are off the line in the upper part, positively skewed. You can see the ones that are positively skewed are more than negatively skewed. That is why overall, the data set is positively skewed. Go down. They can do the same thing also. You can use percentile plot. The trended normal, I have been trying to look for what this one actually means. Go down. Just go down. This one, I'm trying to see what it actually means. But this is box and whisker. This box and whisker is the same thing. It's trying to look for the normality of distribution. Now, the box, the middle of the box is the median. The upper portion of the box is 75 percentile, the third quartile. The lower margin of the box is the 25 percentile, which is the first quartile. So yeah, you just say, okay, the lower part of the box now is first quartile, the middle is second quartile, which is median, the upper is third quartile, which is 75 percentile. The lower part of the whisker is the minimum value, the upper part of the whisker is the maximum value. But we still have some outlier as far as the extreme values. The extreme value that actually, if you look at it, you have one outlier as a lower part, where we have a lot of outlier at the upper part. Of course, that is why eventually it's positively skewed. If it's not skewed, the median should be in the middle of the box. But the median now is closer to the lower part. The distance between the middle and the upper part is more. That shows that it's positively skewed. The upper part is skewed to the right. That is the interpretation of this. Now, there's always what is whisker. The whisker is this one. You know, like a whisker now that somebody's nose hair, like the whisker of animal. So this is box. The whisker is this thread, it marked like thread. This rod is the whisker. So the box and whisker, there's one box and two whiskers on both ends. This is lower whisker, this upper whisker. Somebody say, where exactly is at the boundary? Okay. The boundary of the box, look at it. The blue, the boundary of the box is the lower part of the box is the, look at it, the lower part of this box is the boundary, is the first quartile, 25%. If you look at it, don't mind this one, the plotted here. It's not, this one is not showing, this one is not in percentage. But this one, this place is the 25 percentile. This is the first quartile. The middle is the 50 percentile, which is the second quartile. The upper margin of the box is the third quartile, which is the 75 percentile. I'm receiving text. Let me see. Exactly at the boundary of the box. Okay. Sorry. So what is the whisker? I didn't follow here. I need to understand how text is interpreted. Okay. I think we have solved those ones. So the whiskers are this extension from the box. They are the whiskers. You have the lower one, the upper one. So this end here is showing the minimum. The end here is showing the maximum. So this outlier, those ones are extreme values, and the number you are seeing there is just telling you the position of these values in your computer. If in case you want to check that, as you analyze, you may say, extreme value, why is the extreme value? I want to know and go and check. Maybe it was a mistake. It will show you the number, the position. If you sort your data before you run it now, you sort the data with serial number. Somebody is talking. Jane. So we didn't see you yesterday. So if you have sorted your data set before you run this analysis, you sorted.
And so I even joined. I'm joining from the field.
Okay, that's fine. Well done. Sorry for that. You work so much. So when you if you are sorted with the serial number, so this thing the 100 will be me serial number 100. But if it has scattered, you didn't sort, maybe you go, because if you sorted with other thing before, or the thing sorted is not sorted with the serial number, it will correspond with the number in the computer, the number along the SPSS. So this number is actually the number along the SPSS. But if you are sorted with you sorted it before you run it with the serial number on your data, of course, the serial number of your data will be serialized with the number on the SPSS. So it does, this one is just for you to be able to locate those data sets in case you want to make some correction, you want to know. You know, sometimes you can see an outlier, you don't expect it. You see, there's no value that is as big as this in this data set. You want to go and check which number when you check, so that you can go and check the number on your questionnaire to really know the questionnaire, and then know, okay, where to, if you need to make correction or is it true, adjust it. Okay, scroll down. I think that's the end of this. The boss on which side the last. Yes, any question? Any question? Any question? I thought you wanted to ask question on Shido.
Okay, no, sir. I was just saying that that's the end of it.
Yes, that's the end. Okay, you can stop sharing. Any question concerning what we have just discussed, boss and whisker, how the what do I call it? The stem and leaf. Any question? Okay, no question. Now, I want to share some slides with you so that we can just quickly discuss some things concerning this normality. You can see that this thing is not normally distributed now. Let's just share some thoughts about it. So with this, just talking about how to check for normative, this is what we have done now. Plotting histogram.
Okay, sorry, sir. My hand is up.
Okay, go on. Go on.
Okay, sorry. I'm joining late. Can you just give me a
What? Your connection is bad also. We cannot hear
of
you.
what we're talking about? It looks like I'm lost.
Which one? Okay. If it is only the something, because
Just give me a summary of it. Okay. Okay. Can you hear me now?
I can hear you. Okay, what we just talked about here, I think I even put what I just talked about. Don't worry. Just snapshot 1 minute something, because we will not be able to talk much, because so that it doesn't bring us back. But let me just share my own, because it's the same thing. What we just did to plot the age, look at the normality, we discover that this thing is skewed. The histogram show that the thing is skewed to the right. Skewed to the right means that the mean, when you are plotting, can you see? It's very simple. The base of the graph is the age. As the age increases, can you see 20, 30, 40, 50? What you're having as frequency is the number of people in that category. So if you look at it, as the age increases, small, the number of people in that category increases. That's the way of normal distribution. It will reach the peak age for that group. And as the age increases further, the number of people in the category start going down. That's the way normal distribution works. That's why the shape goes on and comes down. But normally, if it's normally distributed, the one side, the left side of the shape will be a mirror image of the right side of the shape. In that case, that middle, the peak of it, which is the highest, that should have, that value is the mean. And that value is the median. And that value is the mode. Why it is the peak is that most people, that's the one that have the highest frequency, number of people there, the highest frequency, that is the mode. And in a normally distributed data, the mode happens to be the value of the mean and happen to be the one in the middle, which is the median. If you arrange it in ascending order or descending order, the middle value will be that one that's where the people, most people are. The highest frequency will happen to be the middle value. One of them will be, if you arrange it, ascending or descending order, one of those people that have that value will be the one in the middle. And that value will be the mean if you add everything and divide by the total number. That is the characteristic of normally distributed data. But in a situation where there's an outlier, which is example, an outlier is a value that is extremely different from others. It's exactly extremely different from others. What it means that, for example, Dr. Olango was giving an example yesterday. I usually give one example. He gave which makes sense. But the example I usually give is, I say, okay, imagine in this class now, maybe the average age of the people in this class maybe is 38 or 40, and some will be less, some will be more, but the average is 40. If we now have a centurion, somebody that is over 100 years, is joining us in this type of thing, what will happen is that the age in the middle and the mode will still be there, because the one that has the highest, normally the mean, if it's normally distributed, the one in the middle will be most people will be there. But since this outlier, one centurion came now, it doesn't disturb the median. The median will still be there around that place and the mode, but that mean will change because that man has added, that centurion has added a big value. You calculate the mean by adding everything together and divide by the total number. And the total number has not changed. When you now bring it in and now put it there, it will now make the mean to go higher than the median and the mode. In that case, the thing will not be bilaterally symmetrical. It will be flattened toward the right side. It's because the mean is higher than the median. So this graph now, that is what this graph is showing. And if you look at it, look at the data, the mean is 33.2 and the median is 32. So the mean is greater. When the mean is greater than the median, it's positively skewed. That's outlier, positive outlier means an example, a value that is extremely bigger than the rest. The meaning of outlier is a value that is extremely different from the rest, significantly different from the rest. But if it is positive outlier, it's significantly higher than the rest, greater than the rest in value. It will make the mean to be higher than the median. But if the other hand, instead of a centurion joining us, you now brought your daughter, for a 3-year-old daughter, 4-year-old daughter to come and join us. So if you, the 3-year-old daughter is one of us. So because it's contributing small, so it is extremely smaller than the rest of us in age. So at the end of the day, it will slash the mean. So the mean, instead of it, the graph to be flat to the right side, it will be flat to the left side. And when you look at it, the mean will be less than the median. That is negative outlier. That is skewed to the left. So you can differentiate the two now. So that is what you just demonstrated here. Look at it. And we also show stem and leaf plot. The stem and leaf is the same thing as histogram. If you look at the shape, it's only that the stem and leaf is tilted to one side. It's not sitting on the base. It's sitting on the side. If you look at it, the stem and leaf, you look at the way this one goes up and come down. If you look at the way the value of the histogram go up and come down, it's the same thing. You look at stem and leaf, goes up and come down. It's only that if it's the same shape. So the only thing that the stem and leaf give more information than the histogram, because the histogram now you cannot see the value there. But the stem and leaf, they publish this in turnaround. If it's stem and leaf, if it's histogram, you cannot see, just see the shape. Stem and leaf give you the shape, you can bring out the value and write it out. You can write all the value out and go and use the data set. So I explain it. Let me just quickly. You see in the stem and leaf, what stem and leaf means that the last digit is the leaf, the previous digit will be the stem. So in a situation, this situation now, in the previous digit can be 1 or 2 or 3. In this situation, there are only 2 digits for all of them because it's age, and nobody has age over 100 or more. So in that case, there are 2 digits. So the first one is the stem, the second one is the leaf. If you are dealing with heights that usually have 3 digits, the first 2 digits will be the stem, the last digit will be the leaf. So what it does here, look at the frequency. This frequency one means that there's only one in this category, and that one is someone that is less than or equal to 18. The minimum in this data set is 18. But if you look at this second one, 19, this one 9 means 19. This 2 1 means 21. This one there are 8 here. It means 2, 3, 3, 3, 23, 23, 23 in 8 places. This one 8, 24, 24, 24, 25, 25, 25, 25. This 11 of them, 66, 66, 66, 77, 77. That's how it is. So you can copy it out. That is the logic behind the stem and leaf. And when you describe that, we have quarter plot. I've already explained that quarter is three values that divide data set into 4 equal parts. The word quarter is from 4, but there are 3 of them because they divide the value into 4 equal parts. And what are the things that divide? If you put something on 100%, 25%, 50%, and 75%. Because in between them is 25, 25, 25, 25, making 100. So the first quarter is 25%, the second quarter is 50%, which is the median, the third quarter is 75%, which is the upper quarter. So the computer, the normally distributed data set inside the computer has what it does, it tries to plot the quarter with your own quarter to see in a tug of war, if 2 people are fighting, the pulling, if they are sent out from both sides the same, it will be in the middle. So we expect, because the expected value is the quarter for the normally displayed data inside the computer, the observed one is for your own, the one we are having now. So if actually your own is equally normally distributed, this point you are seeing is where both of them meet. They should meet in the middle. Their value should be just meet along the diagonal. But because a lot of them are off the diagonal and look at it, that shows that it's not perfectly normally distributed. And you see that more are along off the diagonal at the upper part than the lower part. So there's skewness to the outlier on the lower part. There are more outlier on the upper part. So that is why eventually, overall, it will be skewed to the right, to the upper part. That is why the mean is greater than the median. You can also do percentile plot. I maybe we'll do that also, because then look at the last one we explained is the box and whisker. This box is still looking at the normal distribution. This box is just showing, okay, the middle of the box represents the median. The lower part of the box represents the first quartile, which is 25%. The upper part of the box, third quartile, which is 75%. So actually the box is showing the three quartile. The lower part is first quartile, 35%. The middle of the box, the line in the middle is showing the second quartile, which is 50%, which is the median. And the upper part of the box is showing 75%, which is the third quartile. The whisker are those extensions. Those are the whiskers. This whisker, the lower part of the lowest part here is the lowest value, and the upper part is the upper value, highest value. So what you are seeing as is scattering, they are the outliers. Outlier, they are the extreme value. You see one outlier down, we have many. That is why many up. That's where eventually it's skewed to the right, to the upper part, because we have more outlier on that side. The value you are seeing there is just telling you the location. If you look at the one Dr. Una show, you see it's different. The value is put in there is different from my own. It's the same as I said. It's the position of this thing in your computer. The position, the number along the SPSS numbering. That's what it's showing you. So that why it's showing you is that if you why is the outlier there? This outlier, I don't know. If you want to check your data, you go back, you'll be able to know the serial number and go back to your questionnaire to check if it's actually true or is it a mistake in entering the data. That's just what it's showing. And that's what you just explained. And I ask question. Want us to go further? No, so I just wanted to.
Yes, sir. I want to understand that STEM. The STEM
It's
itself.
not you that asked the question.
I know usually stands for competency. But I don't know what it stands for in this situation. And why is, because I know that the values are outside it, like they are, that is way ahead. Maybe if you can explain why that is. Thank you.
What is that? What is that? It's outside what? Way ahead or what?
No, there was the box and that box plot, the box and whisker plot.
Yes. Go on. And what happened? What happened to this?
The value. I want to understand what the whisker, what is, because the one, the idea I know of, the one I know of is I used to think it was like the confidence interval, but
no,
in this case, it means a different thing. And I wanted to understand why those other values, if you look at them, they are outside, they are above it.
Maybe you were feeding your baby, because I've explained it 2 times now. You were not just listening.
Hello? So did you get my question?
Yeah, I got your question. I said maybe you were feeding your baby by that time, because
so did you get my question?
I got your question. Let me answer it. Oh, are you people not hearing me? I'm not muted. Is something? Hello? Can somebody hear me? Can somebody hear me? Hello, Jane. Sorry, the network was having problem. I got your question quite right. Hello? Is she there?
Yes, I'm here. Thank you, sir.
I got your question. I said maybe you were feeding your baby by that time, because I have explained 2 times. I first was explaining when Jane came back. I went back to explaining. What I was saying was that that box and whisker you are seeing, the whisker is the minimum and the maximum. It's not confidence.
Is that those? You see that stem? That's
all those extensions.
That's one that looks like a stem. I don't know what it means. Thank you.
I said that
Hello?
this one is just talking of the hand. This one is a distance between this 25 percentile to the minimum. This one is the distance between 75 percentile to the maximum. All this one you are showing, just try to show you just dotting that this outlier that caused the outlier that caused this outlier, their position in your computer. What is causing outlier? This number 95. Now I will open my computer. You see, it's going to be the highest of them. If you remember the age, the highest age is 65, 56 rather for this data set. 56. We're going to see that the computer in my own data set now, that one will be located at number 95 of that computer, of my computer. You know, sometimes it may vary your own because we sort, sort anyhow. Sometimes I may sort my data due with sex. Another person may sort, but it doesn't change the data. But the only thing I can change the position of each value in the computer. It is helping you to know the position in case you want to go and trace it. That's all this 95. In case you want to go and trace it and make the correction, that's just it. So is it clear now? And you will see that this thing is
yes,
skewed.
sir, very clear.
It's not
Thank you so
skewed.
much.
The middle line, 50% should be in the middle of the box. There is not in the middle of the box. So that shows that it's skewed. See, the distance between the middle of the box and the upper part of the box is bigger than the distance between the middle of the box and the lower part of the box. It now shows that it's skewed to the right. If let's say it's skewed to the left now, it's a negative skewness. Is the distance between the middle of the box and the lower part that will be bigger. But if there's no skewness at all, it will be in the middle of the box. So the distance between both of them will be equal. From the middle to the upper and the middle to the lower will be equal. So that is what I use. Okay, let me just share the data set.
I understand. See, the skewness pulls the mean towards one side.
It's not the mean, it's median. That middle is not its median. It's not mean.
No. I was talking generally. No, I know the middle is median. Okay. I was just looking at that. That normality curve.
Let's see. Please, I want to show something. If you look at the something number 95. What do I call it? 95. If you remember, the highest outlier is number 95. Can you see? If you look at 95 for my own even serial number is along the something. If you look at the number 95 on the computer here, is 56, and that's the highest value. That's the highest outlier. It's just locating it. If I now 95, and I say, the serial number is 95 also, because I've sorted is aligned the serial number, is sorted along the serial number. I can go to my questionnaire, number 95. That's to check the value. Is it actually 56? So that is the logic behind that thing. Okay, I think we proceed. Jane, I think we have brought you to speed with what we were discussing, right? Because I just quickly did that because normally I would have, because I want people to quickly get some other thing done. Now,
thank you very much, sir.
Jane, she has left. Okay, yeah.
I am here. Thank you, sir.
Yeah, welcome. So what I wanted to discuss here is now that you see that this thing is not normally distributed, it's skewed. How to check for normality? We have done that. You say histogram, probability plot, contact plot. The only thing we didn't show here is contact probability plot, because it's contact plot yourself. But when you explore, it doesn't, unless you go and check, there's a way you can plot it on your own, in PPP plot. Then quantify normality with number by calculating descriptive statistics, which was what the Korogov-Smirnov test, quantifying it. That's what they did. Korogov-Smirnov and Shapirovic is quantified. So all those plots just give you visual something to see. It doesn't quantify it. You may not know if that skewness is significant. Is this significantly skewed or not? Then when you use the statistic, it will show you. Okay, before I move on, because I just remember something, maybe we just quickly do the percentile plot so that you see the percentile plot is T2 that place analyze descriptive. And you see PP plot. You see that QQ plot? But that QQ plot, they put it under explore. So when you explore, it brings it out. They don't put the PP plot here. There. So you can click on PP plot and put age. Can you see? It's just like, its own, the other one was QQ plot. This is PP plot.
Sorry, we can't see the output yet, sir.
Okay, sorry.
So we can't see.
I always
You may have
forget.
to share it.
Yeah, can you see? Can you see this PP plot?
Yes, sir.
It's just the same thing, like the interpretation is the same.
Yes, sir. Thank you.
PQ plot. So there's no big deal there. So now, let me go back to where I was. Yes. Now that, how do you approach normality when something is not normally distributed? Well, 3 things you can do. You can rely on the robustness of the test and still go and do parametric test, even though you see that this is not normally distributed. A robust, especially if the skewness is not much, a robust test is a test that is still valid when not all the requirements for using parametric tests are made. 2 examples of parametric tests that are very robust are t-test, student t-test, and ANOVA. They are robust tests. That's why sometimes you see some of the examples we even use for our demonstration. You say, look at where we do ANOVA, we use libido. Libido is called a scale of 1 to 10. So sometimes even like a scale, you can do something because most of the time when you ask question, many questions is on a scale of 1 to 5. By the time you calculate average for the group, it will give you decimal. So you can assume, you can use it as you can use parametric tests on it. So there are some tests you can still use even when not all the assumptions are made. Then you can use non-parametric tests, or you can transform data. But this transform data should be the last option. And that's why people don't do it, because when you transform data, the life is never the same. When you transform data, I think I gave an illustration of transformation, because we want to do transformation now. Before I explain this one, I'd like you to understand very well what we are doing. Okay, imagine we have some data set X. I don't like this one, it's so thick. Where is the, X, S square, and square root of S. So let's say these S are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is square of, what is square of 1? 1. Square of 2. We're talking now, it's a workshop. Square of 3. Unmute yourself and talk. Square of 4.
Square of 3 is
16.
9.
Square of
4
5.
is 16. 5, 25. 6, 36. 7, 49. 8, 64. 9, 81. 10,
so
100.
This is not like I cannot write fast.
36.
36. This is
49,
64. This one is 64. 81. And 100.
100.
Yeah. So what is square root of 1? 1. Square root of 2. I know it's 1.414, something like that. 4. Square root of 3, I know it's 1.73. You remember sword? In those in secondary school, sword. Root 2, root 3. Then square root of 4 is 2. Square root of 5 is 2 point something. Square root of 6 is 2 point something. Square root of 7 is 2 point something. Square root of 8 is 2 point something also. Square root of 9 is 3. This one is 3 point something. What I just want you to see here. The distance between x, each of the x is one figure, right? 1, 1. 1 between 1 and 2, 3, 2 and 3, 3, 1, 1. But when you square it, the distance between the square increases. The difference between 1 and 4 is 3. 4 and 9 is 5. 5 and 9 and 16 is 7. This and this is 9. This and this is 11. 13. Can you see? So, whereas the original value, the distance between them is 1, 1, 1, 1. They are square. The distance between their square, because what we just did now is transformation. You don't know. This is the first one is square transformation, power transformation. You do square. So that's transformation. Transform the data. So if it is square root transformation, it reduces the distance. Can you see between this and this? 1 and 2, their square root is not up to 1. Can you see? Look at the square, the distance between their square root are not up to 1. But that the original number, the square, the distance are 1. But the square root, the distance are not up to 1. But the square, the distance is escalating. I just want you to have a picture of what transformation does. What power transformation when you square is to jack up the value. That is when you do square, qubit, maybe you can do qubit transformation, that is raised to power 3. Whatever you do, those are what we call power transformation. When you raise to power, it will jack up the distance between them. It's not apart from jacking up the value. The differences between the successive value is widening the distance. While if you do root transformation, it reduces the distances between the consecutive or different values. So that is just a picture of what I wanted to paint before we just look at what I want to look at. So you see, if something is positively skewed, it's recommended that you do logarithm transformation or you do reciprocal. Reciprocal, if we do reciprocal, 1 over that thing. If you do 1 over something, the biggest will become the largest, and the largest will become the smallest. And the smallest will become the largest, and the largest become the smallest. If you do reciprocal. Then square root, already said it. So if you want for positively skewed, like the one we are doing now, it's recommended that you do either logarithm transformation, reciprocal transformation, or square root. If it is negative skewness, it's recommended you do power transformation. So the logic behind it is this: if something is negatively skewed, you know, we say that there are some outliers that are extremely smaller than the rest. So since by doing power transformation, it jack up the value. So we want to jack them up. That's why you do power transformation for negative skewness. For positive skewness, you know, we have outliers that are extremely bigger than the rest. You know what this one does is to bring them down. But one thing about logarithm transformation that make it very unique, it does both jacking up and bringing down. How does it do it? You see, look at transformation, logarithm transformation scale. Now, look at, let me show the notation. Look at this. Look at, we have logarithm scale is the one up, the one down is hex. So x is the normal scale of numbering. The log hex is the one up. You will see log 0.1 is -1. Log 1000 is 3. In between this log, we have -1, 0, 1, 2, 3. You see 1, 1, 1 different from 1 to 3. The difference between each of them is 1, 1, 1 in log scale. But the corresponding value in ordinary scale, look at from 2 to 3 is 1 in log scale, the difference. But from, look at the corresponding value in normal scale, 100 to 1000. What's the difference? 900. Okay, from 1 to 2 1 and 2 here is just one difference in log scale. Under this normal scale is 10 to 100. The difference is 90. Whereas the difference here is 900, but the difference here is 90. From 0 to 1 on log scale, the difference is 1. Then on normal scale, 1 to 10, the difference is 9. And you see different 9 here, 90 here, 900 here. Now, from -1 to 0, on log scale, the difference is 1. On the normal scale, is 0.1 to 1, which is difference 0.9. And you see, difference of 0.9 here, difference of 9 here, difference of 90 here, difference of 900 here. What do you say? If you consider this from 0 to this 3, you look at the normal scale, what it does here is bringing extremely big value, bring them small. It's trying to say that, look, the distance between 100 and 1,000 is the same distance between 10 and 100, and the same distance between 1 and 10. It's trying to bring extreme value, bring them down. Then on the other side, on the negative side of the log here, what is the, can you see? You see, something that is 0 point between this and this is 0.9, comparing them with this. So what is the eventually extremely small value? He jack them up. It's just like somebody collecting money from everybody now, rich people, and now give to the poor. So it is extreme value, the log transformation bring them down. The extremely small value, he jack them up. So that some of us that were in the training we did on chi-square, and that's going to be the next training next weekend on chi-square, and we also talk about the relative risk and odds ratio. Yeah, I brought logarithm. We were looking at relationship between odds ratio and relative risk. You know, if you remember how we're trying to plot the graph, how if you look at, you want to change odds, compare odds and probability and risk. Probability is risk, odds. Odds is risk over 1 minus risk. So if probability is 0, odds will be 0. If probability is 0.5, odds will be 1. Can you see? So when probability move from 0 to 1 is 0.5, halfway, odds has doubled the movement, can move to 1. When the probability can never be more than greater than 1. When the probability now move from that 0.5 to complete up to 1, the odds move from that 1 to infinity. So the only thing that can normalize it is to change to log. When we now plot log odds, it's normalized. So when we get there, I will not bother you with that one today. By next week, we're going to do is training on all kinds of chi-square, and we run the analysis together with relative risk and odds ratio. So the logic also is well explained there. Now, what I just want you to, what I want us to do now, we want to transform that age. Since it's positive, we want to do log transformation and see the effect on it. So, you want me to do, or somebody want to share? Apart from Dr. Unashuku, who you want to share? Mrs. Oloniyo, can you share your own? You have the data set, right? Skin lesion. You? Is she there? Dr. Taiwo, do you want to share your own this time so that we can do log transformation? Nobody is answering me. Dr. Taiwo.
Yes, sir. My network is not.
Hey, can you share? You cannot share, right?
Yes.
You cannot share.
Yes, I'm accessing it on
my. Only one person all the time. Jane, can you share?
Let me see.
Jane, can you share?
Sir, can I share?
Yes, you have this data file, skin lesion.
For skin lesions, yes, I think so.
Yeah, yes. Share.
Okay, I'm trying to download the file from my email.
Oh, you have not downloaded. Okay, it will take. Okay, let me use my own because. Oh, maybe Ugo. Shidozie. Okay, okay. Dr. Lagri.
Yes, let me share, sir.
Okay. No, Doctor, don't worry. Dr. Lagri has shared. So
okay.
Those are the senior people here. I don't want them to, because within 1 second they can share. But that's why I don't want to call them. If it's just share now, they have share. And Dr. Balogu, if he's here now. Okay. We want to do the transformation, man. Okay. So go to, yes, transform. Go to transform. So compute. Now, the target variable, that is what you want to do is log, you want to calculate log age. Put log age, no gap. Yes, this is great. So your log age will be equal to that we want to look for now. So the log we want to do is natural logarithm. It's not logarithm to base 10. It's natural logarithm. So, and if you look at it, if you go and click on under the function on the right side, come to the function on the right side. Under all, you see all, if you click on now, wait, don't click all. You have clicked, no problem. Immediately you click on, it has listed them. They want to, it's arithmetic, click it, so that I won't be looking for it too much. Click on arithmetic. That's where it will select only the arithmetic down for you. Click on arithmetic, man. Yes, can you see? The natural, you can see the natural log is there. ln is natural log. So click on ln. As you click on it now, great. Immediately you click on it, it gives you something, it throws on the number, normally return to the case, so you just say something here. So move it to, you want to move it up. Click on that arrow that go up. Exactly, can you see? It move it up, and that's a natural logarithm of what? So that's what it has already highlighted that question mark there. That's where you should put it. So yeah, come and click on H here. Yeah, I just move it here to replace the question. That's all. Click OK. You have done the natural logarithm transformation. Click OK. That's great. If you move to the side, let's see the side of your. Can you see? Can everybody see? On the left, right side, rightmost side of the data editor window, you see log H you just did now. That's, you have created a new variable. You have transformed it to logarithm scale. Is it very simple? It's not difficult. Any question concerning what you have done? We want to run it now. We want to do explore it also. When we explore it, we want to see if it's normally distributed. You see that it's still, but it's better than the original. It's not as skewed as the original.
Sorry, sorry, sir. Can he run it again? My laptop is frozen. I have to log in again on my phone.
Okay, okay, Dr. Lagunjoye. So go back again and go back again, man. Or maybe I should run it. Don't worry.
Yes, sir. While he's running
let me
that,
run
I
it
have
so
a
that.
question.
What do you say?
You know, you talked about the robustness of t-test and ANOVA.
Yes.
I wanted to, I wanted to understand the logic. Like, why is it? Like, what makes it the t-test and the ANOVA, like, such that you can actually use it or not for?
Well, to me also, I don't think I have an answer to
you.
that one, but I just know that they are robust tests. If I find answer later, the reason they are robust, I will let you know. They are robust tests because well, I can't really get complete answer. But if you look at it, what we have been doing, you discover that when you run analysis with them and some non-parametric, you know that it is when you don't have option, you even go for. Me, I prefer still using them to the non-parametric, because the non-parametric, they don't have power like and those non-parametric are different type also. Like median test now is not as powerful as the other one. Sometimes you find something significant with this, and the other one, the non-parametric, they don't have the power to get the difference. So if I have more explanation, I will let you know. But they are just, those are the things you consider when choosing what to do whenever your data set is money. Okay. Okay, stop sharing, Dr. Olagunwe. Let me share my own. Stop share. Thank you, ma'am. So let me share and repeat what she has just done. So, so what we did was analyze and transform. So Jane, so you are following now. Jane, is he there?
Yeah, I'm here.
Yes,
Okay,
sir.
Jane,
Yes,
check.
sir. I'm here.
I'm here.
You go to transform. You go to transform. After that, you click on compute variable. When you click on it, target variable is what you want to form. You want to form log age. That is there, log age. So the log age is equal to what you are calculating log age. Log age is equal to what? So what you do is that you now come to the function on the right side.
It's equal to age.
No, log age is equal to what? We have not known. Log age is equal to the expression. That is the expression I will give you. Comment. Now come to the function on the left side. Function group. If you click on her, that was you did before. It will list all the function will be listed down here. If you click on you give all of them and you'll be searching for it better. If you know where it belongs, natural logarithm is arithmetic function. So if you click on arithmetic, so you easily see it. But if you click on her, it will be there. You have to be scrolling down to go and locate it. Then you click on arithmetic, can you see? ln is a natural logarithm, not logarithm to base 10. So ln is natural logarithm. You click on it. When you click on immediately, this thing will come to this box. When you do that, this arrow, you click on it. When you click on it, it moves. You put the ln, logarithm, natural logarithm of what? Put in back here, what you want to do. So its age, you now click on age here and just move it to replace the question mark there. And click OK. It has done for you. And if you want to see it, it's there on the, let me scroll to the end. Can you see the end? You see, can you see the end of the something? Can you see? Log age. It has done the logarithm. Simple. Now, if you want to now do the normality, you want to see if it's normally distributed. How did we do that time? See, analyze, you explore, frequency explore. So it's not age now, it's not age this time, it's log age, logarithm. Because I don't need to go and click, because what I did to go and click histogram is already there, because that was the last operation I performed for each. So all those things you want to do it right here. Yours too, okay. When you do okay, let me share the output, because that is the output. Can you see the I'm coming. Yes, it's the output. Can you see the skewness? You see the skewness is better now. It's not as skewed as the other one.
Yes, sir.
Yes, so it has done some. So you can see the mean. Look at the mean and the median. It will not be too far. 3.4785, 3.4657.
Hello.
You know, the mean and the median are not too.
Say hello.
The mean are not too far. Mean and median are not too different. And but if you see, it's still skewed. But if you look at the test of normality with Kolmogorov, they say that Shapiro-Wilk is actually better, because this one is difficult to please. Yes, Shapiro-Wilk is very better. If you look at it, if you remember for the original age, the p-value was 0.000, 0.000 for both of them, but the p-value has jacked up now. So though it's still skewed, but not as skewed as what it was before. Does it make sense now? So and look at the shape and look at all this. If you look at the all those other things, if you even look at the boss and whisker, even though the upper part is still bigger, but not as prominent as before. If you see the outlier is still that number 95 because I didn't change my distance. Because if the number 35, where you do the transformation, so it's still the biggest one. So that's just it. Any question concerning transformation? Should we continue? Because other transformation you can do, like you may have to go, how do you calculate BMI? Those are the other computation transformation you do. Where is it transformation? That one's computation. Where you want to transform also. You want to, because the other data set, that's what we're going to use for it. The other data set of BMI, that's what we're going to use for to calculate BMI. So should we continue? Because I don't want to be talking to people and people are already exhausted. This is tonight. Are we okay here or should we still? Please. Hello? Opinion from the house. Should we stop here or should we still move further? Because I don't want to be talking and people are more confused.
Bye.
Where is Doctor? Okay.
Bye.
Prof.
Let's go.
With you.
Okay, should we continue? Should we end?
I think that the brain is getting saturated now.
That's why I asked the question. Because I don't want to. Because actually it's from 6 to 8:30, but though sometimes Chris is there, we can extend. No problem. Tomorrow we have. I think we have understood. We have covered the ground. We need to cover.
Yes.
By tomorrow we now cap it off. Whatever remains, tomorrow we concretize them, and with this you should be able to move. What this one is able to do for you, we're able for you to summarize your data, and all some manipulation you can do. That you want to create a new variable, you want to create new variable, you want to arrange all those things. Those are the things we have done. So it will be useful by the time we are now doing something that we want to do specific inferential statistics, like we want to run t-tests. Like next week now we'll be looking at chi-square categorical variable, chi-square relativist odd ratio. So it will be able to help because if they are saying, because some of those things they are not specific things that you do also. Yeah. But many people when they come for the training, we ask them to share, to do they are lost. They say they know how to use SPSS, but if they don't know how to do some specific things, some things are assumed, and that's just it. I see some chat. Can we stop here? Okay. I said that. Okay. So not many people want to talk, but they want to send the chat. Okay, it's okay. I will stop here. I will mail it to us also. I will send the link to us. So please, between now and tomorrow evening, let's watch yesterday's one and watch today's one also, if we have time, because both of them are close to 1 hour and 3 hours video, like 2.5 hours, if you have time. But if you have time to do that, it will be great. So you'll be able to understand very well. And tomorrow we'll now cap it up.